As we as we continue our discussion of polynomial functions, we're now going to talk about turning points and end behavior. Turning points are actually not a new idea. You guys have actually talked about turning points already. We just didn't call them that. A turning point is a point, so an ordered pair, where the graph changes from increasing to decreasing, or vice versa. So this sounds like maxima or minima, which we've talked about in previous sections, and that's exactly what these are. So a turning point, it's correlated with a max or a min, but remember a max or a min was a y value. The turning point is just the ordered pair associated with that max or min. A polynomial function of degree n has at most n minus 1 turning points. And you can think of this as there's one turning point. The graph has to turn around between every two consecutive x-intercepts. So just to give you an example, if we look at this cubic function, degree 3, x cubed minus 4x squared minus 11x plus 30. So degree 3, so we know it could have at most n minus 1, which would be in this case 2 turning points. So if I look at the graph, I see 1, 2, 3 x-intercepts. And between each of these x-intercepts, we can see there's a turning point. So we see there's a max between these two, and there's a min between these two. So the graph is increasing until it gets to this turning point, and then it turns around so that it can cross the x-axis again. It's decreasing until it gets to this turning point, then it turns around so it can cross the third time. Okay, now end behavior. Like the name suggests, the end behavior is the behavior of the graph of a function for large values of the absolute value of x. So this means x is really, really large, either in the positive or negative direction. So really, really large x values or really, really small x values. So this is on the right or the left of the graph, where x is really large or really small. The graph of a polynomial function of degree n with a given a value resembles the graph of its power function with that same a value. So remember, power function, it's that monomial function, that monomial polynomial function. So for large values of the absolute value of x, which is saying on the ends, way right or way left, the graph of a polynomial function behaves like its leading term. So the highest degree term. So in this case, in this generic case, it's going to behave like the function y equals a sub n x to the n. So let's go right to an example to see what this looks like. So the end behavior, it depends on the degree of the polynomial function, whether it's even or odd, and its leading coefficient. So whether that leading coefficient is positive or negative. So our first case is if it's an even degree polynomial, so second degree, fourth, sixth, etc., and has a positive leading coefficient. So an example would be y equals 2x to the fourth plus x cubed minus 6. It turns out that this function is going to behave like its power function, y equals 2x to the fourth, on the ends. So we're looking at the highest degree term, and if it's written in descending order, it's going to be the first term. It's going to behave like that on the ends. Now, end behavior only talks about the ends, way right or way left, really large x's or really small x's. We can't say anything about the middle. So this function, we can say then, it's going to look like a 2x to the fourth function. So remember, an x to the fourth, we learned about our even degree power function, so we know that's going to be parabolic. So it turns out this 2x to the fourth plus x cubed minus 6 is just going to look like a parabola on the ends. So if you guys want to just draw a generic parabola with the middle cut out, so you know, like you'd have a middle in here somewhere. So we can't say anything about the middle, but on the ends, it's going to look like a parabola. So let's look at this example. So let's enter 2x to the fourth plus x cubed minus 6. So we'll graph that, and then we'll graph its power function, 2x to the fourth. And I'm going to adjust the viewing window here. I'm going to go from -5 to 5 on the x-axis. And then I'm also going to go -5 to 5 on the y-axis, and the scale is 1 on both of the axes. So there's our 2x to the fourth. Or sorry, that's the original, 2x to the fourth plus x cubed minus 6. And then, so here's 2x to the fourth plus x cubed minus 6, and here's just 2x to the fourth, the power function. So we can see they're different in the middle, but on the ends, they're both going to look like parabolas opening up. That's end behavior. So this is when it's an even degree, fourth degree, and a positive leading coefficient, +2. Now, let's look at an even degree and a negative leading coefficient. So we can probably imagine that if we make the coefficient negative, it's going to flip that parabola shape over the x-axis. So if we look at an example, y equals -3x to the sixth plus x to the fourth plus x minus 1, it's going to behave like its power function, y equals -3x to the sixth. So on the ends, it's going to look like a -3x to the sixth graph. Well, we remember our power functions that we learned. Even degree power functions look like parabolas, and that negative coefficient means it's going to open down. So just draw generic ends of a parabola opening down. Again, we can't say anything about the middle, but we can say that on the ends, this function is going to look like this, a parabola opening down. Now let's look at the third case, an odd degree. So now we could have cubic, fifth degree, seventh degree, and a positive leading coefficient. So if we look at an example, such as y equals x to the seventh minus x minus 2, it behaves like its power function, x to the seventh, on the ends. So the middle could be different, but on the ends it's going to look the same. So we want to remember that an odd degree power function with a positive coefficient, that looks like that snake shape, like the x cubed shape from our parent functions from the beginning of the course. So if you want to draw an increasing snake shape, but with the middle cut out, so again, it could look like something like this. We know the parent function, x to the seventh, looks like something like this in the middle. So we can't say anything about the middle, but we know on the ends it's going to look like this. So if we want to just look at this one in the calculator, so we'll graph x to the seventh minus x minus 2, and then we'll graph x to the seventh, its power function, so there's the x to the seventh minus x minus 2, and then there's the parent function, that power function, x to the seventh. So again, you can see they're different in the middle, but on the ends they look the same, that increasing snake shape. And then our final case here, if we have an odd degree and a negative leading coefficient. So as you can imagine, if you take this shape and reflect it about the x-axis, you're going to get that decreasing snake shape. So for example, if we have y equals -2x to the fifth plus x cubed minus x squared, it's going to behave like its power function, y equals -2x to the fifth, on the ends for really large x's and really small x's. So it's going to look like a decreasing snake shape, so if you cut out the middle, like this.